So please, the screen is yours.
Thanks, Nicola. Thanks. The screen is mine. Thanks a lot, everyone. Thanks for first of all, thanks to the organizers for the invitation, especially for Max. Second, I would like to apologize that I haven't been as active in the conference as I would have liked to. Long story short, I've been moving from one city to the other, and this week I had some problems connecting, but this just means that I'm going to dive into the conference mostly next week, when I'm going to look at all the talks again. It's not the same, but it's what the boundary conditions I said, Max, the other time ended up happening. And okay, so today I'm going to talk about the Strong Sard Conjecture for analytic sub-Riemannian structures in dimension 3. So this is a topic that I feel is a little bit out of the scope of the conference in a first look. And what I think it would connect, and what I want to try to pass, and the objective of my talk is, first of all, to state what is the Strong Sard Conjecture in a precise way, and then talk about the techniques, because I do feel like the techniques that we use, and the techniques in a practical sense, and how the problem evolved could be useful in other settings, in the settings of the conference. So that's where I feel like the link will be. So okay, so this is I'm going to talk about two works, one in collaboration with Ludovic Rifford, and the other in collaboration with all of the three, with Alessio Figalli, Adam Parusinski, and Ludovic Rifford. So two results. So let me start by giving you the preliminaries. So what essentially is a sub-Riemannian manifold? So we're going to consider a smooth connected, just so that it's path connected, manifold M of dimension at least 3. We're going to assume, just to simplify things, that we have a Riemannian metric over M everywhere. And now the really important point, what is sub-Riemannian geometry, comes from considering a totally nonholonomic regular distribution delta. So by this, I just mean a subbundle of the tangent bundle of constant rank equals to some k is smaller or equal to n. And regular just means that I'm going to imagine that it's going to be generated by smooth vector fields. So let's just look at here some sort of an example. The standard example of today, since we're going to work in dimension 3, so M is going to be R3. Our problem is going to be essentially local, so there's really not much to lose by assuming that everything M is everywhere R3. G, we can always assume, like not always, but for this talk, we can assume that it's Euclidean metric. And what do we mean by this distribution? Well, this distribution here, in this case, in dimension 3, the only possibility is that it's spanned by 2 vector fields, but it's going to be rank 2. So it's going to be spanned by 2 vector fields, x1, x2. And this means that for every point of R3, let me put it here, we're going to have a little, so as I said, a subvector space of the tangent space of dimension 2 in this case. And these 2 vector fields, they are going to be smooth. And since they are going to also generate something of dimension 2, I can assume just by local theory, so by the flow box theorem, that x1 is just equals to the derivative in respect to x1. And here's the nice part. x2 is going to be the derivative in respect to x2 plus a function, let's call it a of x, x3. So by this, we're always going to generate, at least locally here, some open space. I can always assume that my open neighborhood of the origin, I can always assume that the distribution is generated like this. And the fact that it's nonholonomic, which is going to play an important role here, means that if we take the Lie bracket, all of them of delta, we eventually will generate all of the tangent space, all of the tangent bundle, sorry, of the variety that we're considering here. So this means that if we take the span of x1, x2, x1, x2, and so on, we eventually get all of the directions possible, right? So this is what it means, and this gives us constraint about what this A is. So in particular, this A cannot be 0. This would give us a foliation. In some sense, totally nonholonomic means the opposite of a foliation, right? It means that you can go to every single direction if we take enough Lie brackets. And this A here, for example, it could have been, say, x1 or x1 to some power d, or more generally, anything of the form x1, let's call it a tilde of x1, x2, plus something of order in x3, where this a tilde has formal power series which is non-zero. That's the only kind of constraint that we have here. So we have a lot of possibilities for this A. We have a lot of possibilities here for kind of sub-Riemannian geometry that we can consider here. Okay. So the objective of a sub-Riemannian, like what we want to study, like I'm not giving all the motivations coming from either physics or robotics or engineer or even classical kind of motivations, but the idea here is that we want to study the geometry of the trajectories which are tangent to all of this at every point of the distribution. So we can imagine that we are some sort of modeling a space which has constraints, and the constraints are given exactly by this tangent bundle here. So one important object is what we call horizontal paths, are exactly the kind of curves that we're going to admit in this kind of geometry. So they're going to be absolutely continuous curves. This is just so that we can compute its length. We're going to call them horizontal in respect to delta if it satisfies the fact that whenever we can derive, actually, it's going to be in the distribution at that point. So for almost all t. In particular, like since it is being defined over a compact set, since it's being defined over a compact set, and it has a length, so we have that the length is smaller than infinity. This is kind of a consequence of the definition that we're just giving here of horizontal path. And one importance, so what we can imagine is that at every point we'll have some distribution, and the kind of curves that we are interested are going to always be tangent to them. And one important thing that happens here is that since it's nonholonomic, and this was the crucial thing, since after we complete by all the brackets, so if we do enough oscillations, we can go to any direction of the tangent bundle, we actually have that M is going to be horizontal path connected. So this means that for every 2 points of M, there's always an horizontal path between the two of them. So something that is going to be tangent at every point of to this distribution. Okay. So in particular, like you can imagine that in here you can redo geometry from the beginning. We can always ask the questions about geodesics, for example. There's all the questions about geodesics that arrive, and the notion of distance and etc. So what I'm going to talk about is a problem that is related to the source of the difference between the Riemannian and the sub-Riemannian geometry. So I'm going to talk about the paths which are really different between the two geometries. What really is a difference here? What kind of horizontal paths really behave in a different way that doesn't happen in a usual Riemannian geometry? So just to give an idea of things that might happen, right? If we take here, let's say 2 points, and we want to compute the trajectories between them, but our distribution is, for example, flat, then the tendency that we are going to have in order to go up, right, to calculate, for example, to try to have the geodesic here, is that we are going to have to use the Lie brackets to go up. So what our tendency is to oscillate. We're going to do something like this, spiralate. So this explains a little bit why this was the photo of the SRI conference, sub-Riemannian geometry and interactions. This was their photograph representing their conference, because this is the kind of situation that you always expect to happen in sub-Riemannian geometry. So let's try to understand what are these special curves that are appearing that are going to be different. So in order to do that, it's convenient to have some sort of parameterization of all the curves possible. So we're going to look at it as in a local setting. So it can be looked at as a trajectories of a control system in the following sense. So we fix a point, and we're going to denote by xt, xu here, the solution of a Cauchy problem. So this Cauchy problem, you can look at it, first of all, in terms of these vector fields here, which are what span the distribution that we are considering. And then you have some coefficients that we can change. So it's the coefficients in each one of the directions that we have. And this is where we're going to have a little bit more freedom. So these UIs are going to be controls. So they're going to be just contained in some open set of the L2 space here from 0, 1 to Rk. You want it to be contained in some open set because you want the solution to be defined between 0 and 1. So you have some constraints. You cannot take the entire L2 space. But the point in here is that, and the remark is that if gamma is horizontal, then essentially it's going to be the solution of some Cauchy problem like this. You basically, if you derive it, you're going to be able to find a control. You have that it's going to be tangent almost everywhere to one of these xi's, and then you can find one of these controls. And the other way around is also true. If you take any solution of the Cauchy problem, then you're obtaining a trajectory of an horizontal trajectory. A trajectory is almost everywhere tangent to the distribution. Okay. So this gives us some sort of parametrization, and therefore we can consider what is called the endpoint mapping for singular controls, which it's also very important in Riemannian geometry, the endpoint mapping in the usual sense. But in here, like what we're going to control, what we're considering is that we fix this point x, right? And we consider this open set of all of the controls, and we're going to end up in the variety M. So what we're doing is that we have the point x, and then we're going to consider some curve given by this u. So this is the gamma x t x u for some of the u considered, and the endpoint mapping is just the point that is in the end here. This is ex of u. Okay, so it gives us this application that goes from all of the parameterization of all possible trajectories, admissible trajectories, horizontal trajectories close to a point to its endpoint. And the trajectories that are going to be really different here, which we call singular, are the ones which are critical points of this application. So just remind, if you do this for in Riemannian geometry, then there's no critical point. There's enough directions, there's never a critical point there. But in sub-Riemannian geometry, there are many points there which are going to be critical, just because you can imagine that you just don't have enough directions to go everywhere, right? You have a lack of direction. So for some, this is really heuristic, but for some of these controls, you're just not going to be a critical point. You're just going to have a critical point. You cannot have a submersion there. So these are going to be the special cases. So I decided not to talk too much about the importance of this endpoint mapping, but just to have a little bit of a small digression. You can imagine that it's very important for computing geodesics, because what you want to do when you compute geodesics between 2 points is to compute, like, to minimize some function, the function that gives you the distance, under a constraint. The constraint that the endpoint mapping starting from x0 is equal to a certain point. So a critical point, and if you want to do such a thing, right, you want to maximize or minimize a functional under a certain constraint, and you look at a usual differential geometry, what one possible technique you might use is Lagrange multipliers, and therefore every singular path is a critical point, so they are all possible candidates for geodesics. So now you have a huge amount of all of these possible trajectories are candidates of geodesics, and they have to be studied separately. You cannot study it via the methods that are coming from Riemannian geometry. So I hope that I'm kind of motivating you to look at this endpoint mapping and as an interesting object. Okay. So what is the Sard conjecture? The Sard conjecture is about the size of this singular path. So the singular paths, I'm saying that heuristically they represent a difference between Riemannian and sub-Riemannian geometry. So what we want to say is that the singular set, this set of bad points, of bad curves, is small. So what we can do is to consider the critical value, so the image of all of the critical points. Is going to give us some subspace of M now. And the Sard conjecture, kind of motivated by the Sard theorem, is that for every point, this set, the set of critical values, has Lebesgue measure 0. So of course, our theorem does tell us that if the source of the application is a finite dimensional manifold, but in this case, it is not, right? We are in the situation that we are in an open set of the L2 space. So in finite dimension, Sard formula is known to fail. There is a very nice example of Bates and Moreiras from 2001. It's even polynomial, like every entry of their morphism is polynomial. And the comment that I want to do is that for dimension m bigger or equal to 4, there are partial results for certain Carnot groups. So for some class of examples which are very important for sub-Riemannian geometry, but of prescribed ranks and steps. So ranks means the rank of the distribution, and step means how many brackets you need to generate the entire tangent bundle. So I think rank up until 3, step on depends on the rank. Rank 2 up until step 5, rank 3 up until step 3. Like some constraints like this is done by Ledonné, Montgomery, Ottazi, Pansu, and Vittoni, and more recently it has been a little bit generalized by Borato and Vittoni. This kind of setting. So yes.
May I pose a question?
Yes, of course.
What about measure in infinite dimension?
So because here we're not measuring, so this one is going to be in M, so we don't need to measure it in infinite dimension. But maybe I did not understand. So what do you mean by that?
I mean, there's of course no Lebesgue measure in infinite dimension, no?
Ah, right. Yes. Yes. No. Yes. If you take the critical set, then there's no yes. There's no measure there. I don't think we compute the measure of it in terms of the L2 space. Is that like I actually don't know how to answer the question.
Yeah, okay, fine, thanks.
Sorry. Okay. So dimension 4, okay. So I'm going to concentrate in dimension 3. Okay. So in dimension 3, we're going to have there is a special property that I'm going to give just as a black box without motivating it too much, which is what is called the Martinet surface. So the Martinet surface is the set of all of the points of M where the first Lie bracket is not enough to generate the tangent bundle. So just to keep in mind, it's going to be some sort of, I'm not justifying why it is a surface right now, but one can show that it's going to be at least of Hausdorff dimension smaller or equal to 2. So I'm going to try to motivate this by the next 2 slides. But it's just the points where doing just one Lie bracket is not enough. So let's see like that. And the point is that every single horizontal path in dimension 3, one can show that is going to be contained in this surface. So this gives us this is a black box that I'm just going to state without motivating much of its proof. But then the singular paths are going to be all the ones which are contained in this surface. So in particular, the Hausdorff dimension of sigma is at most 2, and therefore the Sard conjecture, as we posed just before, is true. But here we can say a little bit more. The strong Sard conjecture, or the Sard conjecture in dimension 3, is that the set of critical values has 2-dimensional Hausdorff measure equals to 0. This is the Sard conjecture in dimension 3. It's expected something a little bit stronger. Now let's look at a couple of examples of what is going on here. So this is one of the first ones, which is due to Martinet. So in this case here, we have a distribution given by dx1, another distribution given by dx2 plus x1 squared dx3. If we consider the Lie bracket, we're going to get 2x1 dx3. And then it's easy to see that if we look at the span of x1, x2, x3, this is just going to be this span of the x1, the x2, x1, the x3. So the surface where this first, not the x3, sorry. Forgot to give the name. The surface where the set, let's say like this, the set where this subspace, it's not generating the entire fiber, the entire tangent directions are given by x1 equals 0. Right, so at x1 equals 0, we have this Martinet surface. Let's call this x1 so that it's easier to draw. This is going to be the Martinet surface. And I want to pay attention to something like what are the horizontal paths here. And we look at every one of the points, every point that we take, we have the direction x1, which is just going to be transverse to this Martinet surface. And then you have the other direction, which at x1 equals 0 is just the x2. So let's say this one. So this one is x2. So the distribution is always like this. So in the end, the only possible trajectories which are going to be horizontal, so it's going to be tangent to this distribution everywhere, and is going to be contained in the Martinet surface, are lines. These are the only possibilities. Okay, so this is good for the Sard conjecture because for every one of the points, well, I cannot go like the only possibility if we fix one of these x0s here, if we fix a point, the only possibility that you have is to follow this line. So of course, even the Hausdorff dimension of the critical values is going to be 1 because you have to follow one of these green lines and you cannot jump from green line to the other. So you have shown that the Hausdorff dimension is equal to 1 here. A more substantial example here is from Zelenko and Zimtorsky. They were studying this kind of phenomena, and they came up to an interesting example where if we compute the x1, x2, here, if we compute the Lie bracket, then we obtain x3 plus x1 square plus x2 square plus 3 x1 square x3 squared. Yeah. And in this case, if we look just at this part here, oops, the x3, so the Martinet surface is going to be generated by this term here equals 0. This is going to be the Martinet surface. And if we look at this part here of the equation, we see a parabola. Paraboloid, sorry. With the axis here, the x3. And another interesting thing is that along this axis, if we take x1 equals 0, x2 equals 0, then all of this term here is 0. So we obtain the x1, the x2, so we obtain something which is transverse. So we can imagine that because of this, the way that the orbits, once we take the intersection of this distribution, so in here we're going to have some sort of, oops, I wanted to do it in red, a point which is tangent, but on all of the other points that we have, we're going to have a similar situation to the Martinet one, where we cut it transversally to the surface. So once again, we're going to have a line. And we can imagine that because of all of the symmetry, the lines are going to be either periodic or they're going to be oscillate. And this term here that is added is exactly what is needed to break the symmetry and to guarantee that all of the orbits are doing this. Now, if we're looking at the Sard conjecture once again and want to see like what is the Hausdorff dimension of all of the set of points that we can reach with single horizontal path, now we have a problem. Because for this point that is here, we can imagine that every other point on the surface can be achieved by it via a single horizontal path. I can start with whichever point that I'm here, and I can arrive to it just by oscillation like this. But what Zelenko and Zimtorsky showed by hand is that the length of gamma is equal to infinity. So actually, we did say that the horizontal paths, they have length which is finite. So actually, there's no single horizontal path between y and x0, because it will oscillate, but it will never arrive. The length of it is going to be infinity. So they show that for every one of them, for this example, every one single trajectory, there's going to have infinite length. Okay, so this leads us to the object that is used to study this this kind of problem, which is called the characteristic line foliation. So we have, the idea is that we have this Martinet surface, and then for every point, we either are going to have tangency, or we're going to have that it's transverse. So if it's transverse, we have only one possible direction to move. But if it's tangent, you have many. And what is going to happen here is that you have a line foliation where this point, the points of tangency, are singular points of this line foliation. So you have the situation that, for example, you have something like this, it may happen, or you may even happen something like this, just as before. Okay. And the lemma here is that the singular horizontal paths are concatenation of the leaves of finite length of this characteristic line foliation. So now the problem becomes to study concatenations of leaves of this line foliation, and always with the special case of the oscillation, because in the case of oscillation, initially it seems very bad for the Sard conjecture, but if we are able to show that the length is infinite, then it's okay. Now the strong Sard conjecture based on this is that actually we can show that since it's going to be concatenation of leaves, we can expect that the Hausdorff dimension is going to be at most 1. Okay. So the results that I want to briefly talk about the techniques that are used in dimension 3 are the following ones. So first of all, the result of Zelenko and Zimtorsky from 95, where supposing the delta is generic, in particular, the Martinet surface is smooth, so generic in terms of the same infinity-Whitney topology, then they are able to prove the strong Sard conjecture. They're able to prove that the critical values have Hausdorff dimension at most 1. Then in our work with Rifford, we showed that just with the hypothesis that the Martinet surface is smooth, then we can show just the Sard conjecture, not the strong version, but just the Sard conjecture itself. So here, avoiding like special points of the Martinet surface, we are able to obtain some result. And finally, the last result that I want to talk about, or at least give an idea of the techniques in 2 minutes, is with Figalli, Parusinski, Rifford. In that case, if we assume that everything is analytic, so M and delta are analytic, then we can prove something much more. We can prove that the critical values are countable union of semi-analytic curves. And in particular, what we get is that the dimension of the set is smaller or equal to 1. So under this hypothesis here of analyticity, we don't need to be generic anymore. Then we get the strong Sard conjecture. As an application of this, we are able to show that all of the geodesics are smooth for in the analytic case in dimension 3. Okay. So let me just give a. So I started 2 minutes. Yeah, so we have 2 minutes. So let me just give you an idea about the techniques, which is what I promised to do. So Zelenko and Zimtorsky, in that case, they use the fact that that is generic to show that, well, then the Martinet surface is smooth, and the singular points of F are one of 2 kinds, either saddle points or focus points. And the techniques, and for the case of focus points, they show, again, by hand, by making computations with normal forms, that the length of all of the trajectories are infinite, so showing what we wanted. And the techniques that they use are normal form and transversality theory. Now, in our first work with Ludovic, what we remark is that if sigma is smooth, then we are able to control the divergence of the vector field that is in here. And just this means that we can control the divergence in terms of the norm of the vector field itself. And just to give you an idea of what does this mean, if you look at the spiral, the divergence is what control how you contract, and the norm here, the integral of the norm, is going to give you the length of the curve. So you're saying that the contraction rate is bounded in some way by the length, and in other words, you can show that you cannot contract in infinite length. You cannot have this contraction in finite length. And in here, the techniques is differential topology and measure theory. But what I wanted to point out is kind of the last step here, where we're going to have to use things where the Martinet surface is not smooth, and how we are going to pass from generic to something which is not only generic but analytic in general. So first of all, the difficulty when it's not. So I don't want to pass too much. So let me actually just go directly for the techniques. So just to say what we do in the case of analytic is that we will have two parts of it. So just let's specialize to the case of oscillation. So the case that we have something like this, and we want to show that all of the trajectories have infinite length. So in this case, we are going to have two ingredients. The first one is that if delta is analytic, then there exists one trajectory of finite length. All trajectories have finite length. And in here we use techniques coming from singularity theory and analytic geometry, much in the sense of the Hilbert-16 problem. So resolution of singularities, regularity of transition maps, quasi-analytic classes. And on the other hand, by using the fact that it's nonholonomic, we're going to show that almost every trajectory has infinite length. And in here, we're going to use symplectic geometry and measure theory. And just the point that I wanted to kind of say is that the fact the extra hypothesis of being analytic allows us to have access to all of this extra techniques which were developed in the last century for it, and which can deal with any kind of, for the analytic case, but any kind of degenerescence of the distribution itself and of the vector field itself. So that's all that I want to say. Thanks a lot for your attention.
Thank you very much for the interesting talk. So, are there any questions, comments? Yes, please. I'm not sure your name is Zadra. Please.